Hello my dear students, welcome to the lecture series of methods of differentiation. This is our lecture number 8 and in this lecture I am going to discuss about the differentiation process of a symmetric infinite series. So let's get into the video. So here I am going to start the chapter by taking some examples only. So let's begin with the example. If y is equal to x to the power x to the power x to the power up to infinity, then find dy dx. And here you see the series involving here x power x power x. This is symmetric. This types of series is called a symmetric infinite series. That means an infinite series in which the terms are repeated again and again, again and again. So those types of series are known as symmetric infinite series. And how to differentiate an equation or an expression or a function having symmetric infinite series, and that will be cleared from the examples I am going to solve today. So let's go to the solution of this problem. Y is equal to x to the power up to infinity. Then we begin with this given expression y is equal to x power x power x power so on up to infinity, and we know that from an infinite series, if we eliminate one term from the series, then the series remains infinite. Or in an infinite series, if we increase one extra term, if we add one extra term in the series, then also the series remains infinite. So here you see y is equal to x power x and so on, it will be up to infinity. So if you do not think about this x, then the power, that mean the remaining section x power x and so on, that term can also be taken as y again, because in the question it is given that y is equal to x power x. So do not think about this x, and the rest of the terms can be taken as y again. So that is why I am writing here y is equal to this x is remaining same, and the powers x power x, this is up to infinity, can again be written as y. And already we have solved this problem in the earlier chapter, previous chapter. So taking log here, so log of y is equal to y into log x. This power will be come in front of log. Then differentiating with respect to x, so left hand side is simply 1 by y dy dx, this one 1 by y dy dx, and equal to, here it is a product function y into log x, so y derivative is dy dx, log x remaining same, plus y remaining same, and log x derivative is simply 1 by x. And now collect the terms dy dx in the left hand side. So dy dx is common, here it is remaining 1 by y, and from this term going to the left, so it is negative, dy dx is already taken common, so log x will be there, is equal to, this term is only y by x. Then taking LCM here, so dy dx into taking LCM y, so it is 1 minus y log x only, is equal to, right hand side is as it is, just take cross product, this y will go here, that means it is y square, and this term numerator will come here, x into 1 minus y log x. So that is y is equal to, this y is going here, so y square, and this term is coming with x, that is x into 1 minus y log x, and that is the solution for the problem. And this problem can also be done in another way also, that is by not taking logarithm in this way. That means you can write this expression x to the power y in the power of e to the power log as like this. You see here y is equal to x power x, this is the given expression, and so y is equal to, it is simply x to the power y, and so y is equal to, since here it is variable in the base and power, therefore we can write this term x to the power y as e to the power log, then x power y is taken here. So e power log, it is actually will remove, that means the term remains only x power y, that is x power y can be written in this way also, because it is a property of logarithm. Then y is equal to this power y will come in front of this log, that means e power y log of x. So that is equal to derivative dy dx is equal to e power some function, derivative is the function itself, we know the formula for e to the power x, it is e to the power x itself, and here y log x is considering as x, so e power x derivative is e power x itself, but it is not actually x, it is y log x. So by chain rule you are to take the differentiation of this power again, and so it is a product function y into log x. So y derivative is dy dx into log x remaining same, plus then y is remaining same, x derivative is 1 by x, you know that one. So dy dx is equal to, again you see this term was actually this term, and that was actually this term, and this term is nothing but x to the power y. So the whole term, this can be replaced by x to the power y. So we write here x to the power y, and the rest of the terms are remaining same only. And then take dy dx common by taking this term in the left hand side. So dy dx, this is 1 remaining here, minus this term will be minus, so minus x power y into log x, this log x, equal to, on the right hand side, x power y into y divided by x, this one. So that is implies dy dx is equal to, this x power y was actually y, you see x power y is y, so it is simply y square divided by x is here, then 1 minus this term actually, but x power y is y, so I am writing directly here y log x. So you may also solve the problem in this way also. Okay, so let me take the next question. This, if y, find dy dx if y is equal to this expression. This is also a symmetric infinite series, you see, because same term is repeating and repeating again and again up to infinity. Same term, that is root over sine x again plus root over sine x plus root over sine x. So this is actually a symmetric infinite series. So in this problem also you take the differentiation by taking this one. First of all you write this expression, y is equal to this. So y is equal to the expression given. I am going to take square on both sides to remove this root over sine actually. So y square will be equal to, this sine x will remain same, that means this root over sine will remove, so sine x plus, and the terms remaining is root over sine x plus root over sine x plus so on up to infinity. And this is actually, since the term is up to infinite, therefore this total term can again be considered as y, because root sine x plus root sine x plus root sine x and so on up to infinity is taken as y, therefore this terms can also be taken as y. As in an infinite series, I already told you that in an infinite series, if you remove one term or if you add extra term in the series remains again infinite, and that is why this is, though in this series one term is not here because one term is separated from this root over sine, again this is sine x, and the rest of the term is again root sine x plus root sine x, and again you take here root sine x and up to infinity, therefore this total term can be taken as y again, because this is equal to y given in the question. So we will get actually y square is equal to, this is sine x plus these terms can taken as y. Now take differentiation. So differentiating with respect to x, left hand side is twice y dy dx only, y square is twice y, and for y dy dx. Sin x derivative is cos x plus y derivative is dy dx only. Then dy dx shifted to the left and taking common. So dy dx is common, it is twice y and then minus 1 is equal to, this is cos x simply. So then dy dx is equal to cos x divided by this term, twice y minus 1. And this is the solution for the question. And you solve this question for as a homework. If y is equal to, just root x is given in place of sin x. This sin x, sin x, sin x is replaced by x, 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 and the answer will be this one. Process is same, and I think you can solve this problem, and hence this question is homework for you. So let me take the next question, number 4. If y is equal to e power x plus e power x plus e power x plus e power x and so on up to infinity, and it is again a symmetric infinite series because the term e to the power x is repeating again and again up to infinity. So this is also a symmetric infinite series, and you are to prove that dy dx is equal to y divided by 1 minus y. So very simple, we start with this given expression. So let's take the solution. We have y is equal to this expression, and y is equal to, you see, e to the power x. If you remove this term, the rest of the term is again you can take as y. So y is equal to e to the power x. This e to the power x is here, and the rest of the term, you just think about this. You do not think about this term. This term. So the rest of the terms, is it not again equal to y? So that is why I am taking here y is equal to, this y is remaining same, equal to e to the power x is this term, the term we are removing here, plus, and these all terms can be taken as y again, taking log on both sides. So log y is equal to x plus y into log e actually, but log e value is equal to 1, so I am not writing here. So log y is equal to x plus y is our expression now. Now take just differentiation only. So differentiating with respect to x, so left hand side is simply 1 by y dy dx. It is 1 by y dy dx, and in the right hand side x derivative is 1 plus y derivative, it is simply dy dx. So take dy dx in the left hand side, dy dx, this term is 1 by y minus this term is 1 because dy dx is taken common, so minus 1 is equal to 1 is already here. Now take LCM here. So dy dx whole into y is LCM, 1 minus y divided by y is equal to y 1, and so take the cross product. So y by 1 minus y, simply y by 1 minus y. So this is the solution of the question. I am erasing this. So let me take the next question, number 5. If y is equal to sin x divided by 1 plus cos x divided by 1 plus sin x divided by 1 plus, and so on up to infinity, and you see very sincerely here from where the series is again repeating, you see the series y is equal to sin by 1 plus. So here you see this is repeating from this line, sin by 1 plus. So these terms you see here, actually these terms can be considered as y. Okay, so I am writing that one. So this is the given expression, y is equal to sin x divided by this one, then y is equal to this sin x remaining same, 1 plus cos x by 1 plus, these terms are actually y, these terms. Okay, so 1 plus y. Now simplifying here, taking 1 plus y LCM here, so that 1 plus y is multiplied with this one is 1 plus y, then plus this cos x, and 1 plus y will go to the numerator as 1 plus y, and into sin x is already there. So this is our expression now. Now you take a cross product, you do not take differentiation directly here, because if you take differentiation directly here, then dy dx terms will come in the numerator, then you are to take cross product, then you are to take the terms involving dy dx in the left hand side, so that will be a lengthy process. So I am not using that process. As well, if you take derivative here directly here, then denominator will be whole square, but you see the expression to be proved here, you see the denominator is not square term. So therefore we do not take differentiation here directly. Before that I am going to take some calculations or simplifications here by taking a cross product before differentiation. So it is simply y plus y square plus y cos x, y plus y square plus y cos x is equal to, this is numerator only, mean 1 into this one, that is 1 plus y into sin x. Then take differentiation. So differentiating with respect to x, left hand side this y is dy dx, y square is 2y then dy dx, plus this is a product function, so y derivative is dy dx, cos x remaining same, and cos x derivative is negative, so I am already taken here negative, y remaining here, and cos x derivative is minus sin x, minus is taken here, is equal to, on the right hand side it is again a product function, so 1 plus y function derivative is simply dy dx, because 1 is 0 and y is dy dx, sin x remaining same, plus 1 plus y is remaining same, and derivative of sin x is simply cos x. Now we are to collect the terms involving dy dx, that means this term, this term, this term, and this term, and other terms will be shifted to the right hand side. So I am taking common dy dx. From this term we will have 1 only. From this term we will have twice y only. From this term we will have cos x, and from this term it is coming to the left hand side, so it will be simply minus sin x. This term is already there, 1 plus y cos x, this is, and this negative term is going to the right hand side as plus y sin x. Then just divide by this term here. So dy dx is equal to 1 plus y into cos x plus y sin x divided by this whole terms. Okay, so that is the solution for the question. And I am erasing this, you see. Okay, so let me take the next question. If y is equal to, this is cube root of log x plus cube root of log x plus cube root of log x plus so on, this terms is repeating and repeating again and again up to infinity, and you are to prove that dy dx is equal to 1 by x into 3y square minus 1. This is our question. So we will begin from this given expression. Okay, so I am writing that lamp. So y is equal to this one. So as we have done in a problem just done earlier in the first or second slide, I think. So in the second slide we have done this types of problem. So here also, first of all, you try to free this log x from this root over cube root over sign. So to remove this cube root, we are to take whole cube on both sides, so that this cube root will remove. So y cube will be equal to this cube root will remove. So log x is remaining there, and the other terms will be as it is. And you see, since this is an infinite sequence or infinite series and symmetric infinite series, that can be taken as again y. So you replace this whole terms as y. So y cube is equal to log x plus these terms is a symmetric infinite series, therefore this can be taken as y again. Now you take differentiation. So differentiating with respect to x here, y cube differentiation is 3y square, and for y it is dy dx equal to log x differentiation is 1 by x only, plus y differentiation is dy dx only, simply dy dx. So then take dy dx in the left hand side and common. So dy dx is common. From this term it is 3y square, and from this term it is minus 1 because it is going to the left hand side, and dy dx is taken common, so the term is minus 1 remaining there, is equal to, on the right hand side, 1 by x is there. Now just divide this, that will be the answer. So dy dx is equal to 1 by this one. So that is the solution for the question. So the next question is number 7. If y is equal to cos x plus 1 by cos x plus 1 by cos x plus 1 by cos x plus so on up to infinity, then prove that this one, dy dx is equal to y sin x divided by cos x minus twice y. So here you see it is a continued fraction as well as a symmetric infinite series. So the series is repeating from where that the series is repeating from where that is necessary, and that is important. So it is cos x plus 1 by this terms is actually y. Okay, so begin with that line, y is equal to cos x plus 1 by this total term is remaining same, and the series is repeating from here cos x. So this whole terms can be replaced by y. So y is equal to this cos x plus 1 by y only. Take a cross product. So y square plus y cos x plus 1. Then differentiation. Differentiating with respect to x. So it is twice y dy dx. This is product function. So dy dx into cos x minus, because this cos x derivative is minus sin x. Y is remaining same, and cos x derivative is minus sin x. Minus is already taken here, and 1 is alone constant, so derivative is 0, and I am not writing here. Now just collect the terms involving dy dx. So dy dx is taken common, so it is twice y, and it is minus cos x, because it is in the left hand side, minus cos x is equal to, this term is minus y sin x remaining there. So just divide by this term on the right hand side. So dy dx is equal to this minus y sin x divided by twice y minus cos x, and this minus can be removed. by taking negative common in the denominator. And if you take denominator negative common in the denominator, then it will be cos x minus twice y, this one, and that negative sign and this negative sign will be remove each other, and so that is the answer for the question. So the next question is number 8. So this is our question now. If y is equal to root x whole power root x whole power root x whole power root x and so on up to infinity, then we are to prove this expression. Okay, so here again you see this is a symmetric infinite series. Actually you should give an infinite sign here. It is a typing error only, so you give one infinite sign here. So this is a symmetric infinite series and we are to show this expression. So you see the series is repeating from this line, from this one. You just do not think about this root x. The rest of the term can again be taken as y. So the total term is actually y is equal to root x whole power y only. Okay, so I am taking that one. So y, this is the given expression. So y is equal to root x whole power, this total terms is again y. So to solve this problem we need logarithm, because the base is a variable and the power is again a variable. This power and this base both are variable. So we are taking log. Log of y is in the left hand side is equal to, on the right hand side, this log y will come in front of log. So y log, that term is root x. Root x means actually x to the power half. So that half will also come out of the logarithm. So this is implies log y is equal to, this half is coming in front of log, so half y into log x. This is our expression now. Now I am going to differentiation, to take differentiation in this line. So differentiating with respect to x, left hand side is simply 1 by y dy dx. So 1 by y dy dx. And on the right hand side it is 1 by 2 constant number remaining same, and it is a product function. You see, this is a product function. So y derivative is dy dx, log x remaining same, plus half is constant remaining same, so half, and y remaining as it is, derivative of log x is simply 1 by x, because half is constant. So this half y derivative is dy dx, log x is same, plus this half y remaining same, log x derivative is 1 by x only. So collect the term dy dx in the left hand side. So the terms are 2 by, this 2 is taken as cross product here. So 2 by y dy dx is equal to, this is dy dx log x, plus this 2 is already taken as product, and it is the term y by x only. This term is y by x only. Actually I am taking a multiplication with 2. This total expression is multiplying by 2, and then take dy dx common in the left hand side. So dy dx is common. Here 2 by y is there, and this term is minus log x, because it is going to the left hand side, minus log x is equal to, the right hand side is already y by x, and take LCM here. In the proof part you see x is multiplied with dy dx, so I am taking a product by x in this equation. So x into dy dx into, taking LCM here, so y is LCM, 2 minus this is y log x, this is y into log x, so this one is equal to, x is already taken as a product, so this x is cancelled, simply y is remaining on the right hand side. This y will go to the numerator, that means y square, and this term will come in the denominator as like this. So x into dy dx will be equal to, y is going there, so y square, and 2 minus y log x is coming in the denominator, and that is here. And so this is the proof of this problem. Okay, so the next question, number 9. If y is equal to a power x to the power a power x to the power a power x and so on up to infinity, then we are to prove that this expression. Okay, in this question also you see the terms are repeating from here. A power x is, do not think about this a power x. The rest of the terms can again be taken as y. So we write that given expression first, y is equal to this. So y is equal to a power x, this is remaining same, and the rest of the terms can be taken as y because it is a symmetric infinite series. So this problem is again base and power are variables, so we should take logarithm here. So log of y will be equal to this x power y will come in front of log. X power y log of a is there. And so this x power y base and power is again variable. Therefore we are to take again logarithm. So log of log y, left hand side was already log y and I am taking another log. So it is log of log y is equal to, on the right hand side, log of x to the power y is simply y log x. This product is converted to plus and this term is log of log a. Just using the property of logarithm. It is product here. So log of x power y plus log of log x. But log of x power y is simply y into log x plus this log of log a is remaining same. Now you take the differentiation. So differentiating with respect to x, in the left hand side here, first log derivative is 1 by this log y, then this log derivative is 1 by y, and for y is dy dx. So 1 by log y for this log, 1 by y for second log, and dy dx for this y is equal to, it is a product function, so y derivative is dy dx, log x is remaining same, then plus by property, then y is remaining same and log x derivative is 1 by x. And you see this log of log a is actually a constant term because a is constant, so log a is constant, log of log a is also constant. So derivative of this log a is 0, I am not writing here. Then you take dy dx common in the left hand side. So dy dx is common. Here 1 by y log y is there minus this log x is here because this term is going to the left hand side. So will be a negative number. So minus log x is here. Dy dx is already taken common. And is equal to, this term is simply y by x actually. So I am writing y by x. Then take LCM in the left hand side. So dy dx, it is y log y, this one is remaining same, minus, so it is y into log x into log y, so y log x, this y log y into log x, this one is equal to y by x is already here, is implies, just take cross product, this term is coming with this x and this term is going with this term. So it is y into y square, this log y is remaining same, x is already here and this term is coming here, and that is the solution for the question. And this is the proof, you see, this is the proof. And this is the end of this chapter, and you may take some more examples from different books and try to solve these types of problem having symmetric infinite series. And there is no other way. This is the simple way to differentiate a symmetric infinite series, differentiative function involving symmetric infinite series. So this is the way. So we finish this class today here, and in the next class we should begin the chapter parametric differentiation. That means differentiation of parametric function. So till then, thank you very much.